Hello, we're going to be taking a look at an example of inductive and deductive reasoning and how we can use it to prove a conjecture. The conjecture that we're going to look at specifically today is the difference between consecutive perfect squares is always an odd number. We can prove this inductively by finding a bunch of examples that work or a pattern that works, or we can solve it deductively by making sure that it works every single time with every single value of a perfect square. So let's take a look at some examples here. Well, first of all, let's put the perfect squares up there on the screen. We have 1, 4, 9, 16, 25, 36, 49. Okay. This conjecture says that if we take any two of them, which are side by side, subtract them, we're going to get an odd number. Well, inductive reasoning, let's see if it works. Let's try a few. Well, let's start with 4 minus 1. 4 minus 1 is 3. Is 3 an odd number? Yep, I would say it is, and math would say it is. So therefore, yes, that works. Now, we can't just base this on a single example. We need a few. I'm going to recommend at least 3, okay? But more is always better because then it shows that there's more certainty that it's going to happen. So let's do a second one. 9 minus 4. These are the next two. Okay, that gives us 5. Well, that is also odd. So yes, this is in fact true for that too. 2 out of 2 is looking pretty good. Let's go for a third one. 16 minus 9 is 7. 7 is also odd. So therefore, we have 3 for sure. I'm going to use a fourth one. I'm just going to do the next one here just to show that it still works for that fourth one. And 9 is also odd. So then that is in fact true. Inductively, we can say that there is a pattern that is showing this conjecture is true. Okay? We can't be 100% certain because we have not checked every single one of our perfect squares, but based on the pattern that we're seeing, this looks like it will be true. All right, that's inductively. Okay? And that's as far as you need to go. We don't have to go any farther. We've shown that proof. We can now show it deductively and show that every single time that we do consecutive perfect squares, okay, then we're able to, that it will in fact be an odd number. So let's start off with a couple definitions first of all. Firstly, our consecutive perfect squares or consecutive numbers that we're going to use are x and x plus 1. X being any number and x plus 1 being the next number. So let's just visualize here. I'm going to use the number 5 for x. So we have 5 and 5 plus 1, which is 6. So there's our two consecutive numbers, but now we need to make them consecutive perfect squares. So 5 squared and 6 squared. 5 squared being 25, 6 squared being 36, if we want to think of it in the inductive sense. All right, so x squared and x plus 1 squared. If we subtract these two, are we going to get an odd number? And that's what we're looking for. So let's put this into a subtraction statement. Let's always do the biggest one minus the smallest one. So we're going to do x plus 1 squared minus x squared. And so we have these two numbers being subtracted. Let's spread this out a little bit. X plus 1 squared is x plus 1 times x plus 1. And x squared is just x squared. And now we need to do still a little bit more algebra. Yeah. All right. X plus 1 squared gives us x squared plus 2x plus 1. And then we're still subtracting the x squared at the end. All right. Now, at this point, we can't do any other multiplying. So now we're going to combine all of our like terms. We have an x squared and a negative x squared, or x squared minus x squared, which is going to actually cancel out and give us 0. And we're left with 2x plus 1. Now, 2x plus 1, 2x is an even number. If we add 1, it becomes an odd number. So by definition, this is an odd number. Doing this work here has proved that our answer to this question, or this conjecture, is in fact always going to be an odd number. Okay? It's proved that no matter what two consecutive perfect squares you use, okay, start with any number for x. Now again, that has to be a whole number, or an integer actually. We're going to get a an odd number as the answer. Okay, you can try it out for any single one. Do it as big as you want for perfect squares. It's going to work every single time. This just proves it, and that's a deductive proof. I hope this has helped you. Thank you for watching. All the best as you work through any questions you might have.